Hello friends, welcome back to my channel, Physicist Buddhist in California. It's been a while since I posted my last lecture on physics. So those of you who have seen my lectures, I talk about quantum physics and quantum field theory in general. I try to showcase well-known books, very famous classic books in this field. So continuing that, today I'll talk about another book. This is a very famous book. It's called A Guide to Feynman Diagrams in the Many-Body Problem by Richard D. Mattuck. I hope you can see the title. Okay, so this book was published back in 1960s and it became an instant classic and has been in print ever since. It's a, if you see, it's a paperback book, so it's available for a very small, low price. So if you feel like buying it, it's not a very expensive book. Other books in quantum field theory are quite expensive. The ones that I have talked about previously, they can cost up to $100. So this book you can buy for less than $20. So what is this book about? As the name states, Mattuck wrote this book as an introduction of Feynman diagrams in condensed matter physics. So let's take a step back. What are Feynman diagrams? So if you watch one of my earlier lectures, Feynman diagrams are the standard method of solving problems in quantum field theory. And most of these problems, the theory itself began in particle physics. So quantum field theory was invented as a mathematical process to solve problems in particle physics. And the most famous was quantum electrodynamics, where the theory quantum electrodynamics describes the behavior of electrons and their antimatter partners, positrons, their interactions and how they interact with each other by generating and absorbing the quanta of electromagnetic field, which is known as a photon. So that's how the theory began, and it took years for theory to be refined. It was first proposed in late 1920s. It took more than 20 years to resolve the mathematical problems and to make the theory give finite results for finite physical systems. And if you look at my lecture on the book on quantum field theory by Michael Peskin and Schroeder, then you'll see basically that's the standard textbook for solving problems in quantum field theory, and that was a classic book of 20th century. In 21st century is Quantum Field Theory by Matthew Schwartz. I have given a lecture on that also, and that's the standard book in 21st century so far. 21st century is still pretty young. So this book, you could say it's the same, it did the same for condensed matter physics in 20th century. It's probably one of the best books for condensed matter physics in 20th century. There are other books which are probably more useful for calculating quantities, but this book, the strength of this book lies in that it's very easy to follow. The way Mattuck writes, he's basically having sort of a conversation, and he introduces gradually more complex and intricate concepts. And so if you are learning the subject, you want to learn the subject almost from the scratch, then this is the right book for you. So the major difference between quantum field theory in particle physics and quantum field theory in condensed matter physics is in the energy domain. In particle physics, the energy domain, it basically goes all the way to infinity. So you have to assume that a particle can have energy from anywhere from the mass energy of an electron, which is about 500,000 electron volt, all the way to Planck scale, which is 10 to the power 19 giga electron volt, and even beyond that. So all the way to infinite energy. But in condensed matter physics, nature kindly provides a cutoff, so you don't have to consider all that. That's what, by the way, makes quantum field theory and particle physics so difficult, because you have to handle the integrals which diverge in the sense that energy can go to infinity. Now, in condensed matter physics, nature has kindly provided a cutoff, and that is the lattice constant. So, for example, you're studying some system. Let's say you're studying superconductivity. Now, superconductivity arises in materials which are normally crystalline, which means there is a crystal, and you understand what everybody knows probably what a crystal is. So, crystal is basically periodic arrangement of atoms or molecules in space. So, by its very nature, a crystal poses a cutoff on the theory. So, the lattice constant, which is the length of a crystal. Let's say you have a cubic crystal. So you have a cube is in 3 dimensions, and all three sides the cube has the same dimensions. Then the length in any dimension is the lattice constant. So that acts as a cutoff for theory in condensed matter physics. So the Mattuck's book, it basically provides a complete introduction right from the starting from the scratch. What are Feynman diagrams as adapted to condensed matter physics? So, like I talked about, quantum electrodynamics, which is a standard theory in particle physics, which includes 3 things: electron, positron, and photon. So, in condensed matter physics, you have electron, but you don't have a positron because the energies are too small. So, you have what's known as a hole. So, what a hole is in condensed matter physics, it's an absence of an electron. This electron has a negative charge, so a hole has a positive charge. Okay, so electron positron symmetry is replaced by electron hole symmetry. And in condensed matter physics, you can have a photon, a very low energy photons, but one is more interested in a crystal in something known as a phonon. So what is a phonon? Phonon is a quantized excitation of an atom, periodically atom arranged on a periodic lattice. So an electron, say for example, you're studying superconductor, like I said earlier. So you want to understand how electrons come together and make what's known as a Cooper pair. That is at the heart of superconductivity. 2 electrons, in spite of having the same negative charge, can temporarily come together to make a pair, a bound pair, which is mediated by these phonons. So this is what happens. The electrons interact with the same phonon, and with that, this indirect interaction mediates the interaction between 2 electrons, and they make a very weakly bound pair, what's known as Cooper pair. So so coming back to our case and point that we're talking about superconductivity, so you are going to have, what are the quantities you're going to have when you apply quantum field theory? You're going to have an electron, a hole, and a phonon, which is in complete symmetry what you have in a quantum electrodynamics: electron, positron, and a photon. So you have here electron, hole, and a phonon. And then from that point onwards, you can use the same mathematical machinery that Feynman developed for particle physics. It is adapted to condensed matter physics also. And the good thing is that the theory is much easier to handle. What's the mathematical term that I've talked about in my earlier lecture? Renormalization. So renormalization was the key to developing a quantum field theory that gave finite results for physical systems. So in condensed matter physics, this is much easier because nature kindly provides a cutoff, so you don't have to let the energies go all the way to infinity. And using this lattice constant as a cutoff, you can handle these Feynman diagrams. So if you're interested in learning more about it, there's a lot he talks about. So I have just scratched the surface, but please look at this book, and it's a very useful book. It's very, very well written and very interestingly written. It's probably one of the few books on quantum field theory where the author actually talks about Buddhism. So that's another interesting thing, that 2 very different, widely separated concepts are brought together in this book. Okay, I hope you enjoyed my lecture, and if you have any questions, please look at the link below. And thanks for your time and attention, and I hope to see you again in the near future. Thank you. Have a good day.